Hello and welcome to the start of Redox. This is chapter 4 in our textbooks, and some of it carries on from last year. Let's just go through what the study design says we need to know about Redox. So, just to highlight a couple of little things, what we need to know about Redox is that Redox is all about electrons transferring, electrons moving from one thing to another. Later on, we'll do acids and bases, and that's about protons moving. Redox is about electrons transferring. We need to know and be able to spot when reduction and oxidation reactions are occurring. We need to be able to look at them and tell people whether they are reduction, oxidation, or neither. We also have to be able to spot what is the oxidizing agent, what is the reducing agent, the oxidant, or the reductant. We'll get there. Also, we have to be able to do oxidation numbers. Now, that's something we should have started doing or learned or at least seen in year 11, so we should be okay with that. And we also have to finally have a look and see if we can recognize conjugate reducing and oxidizing agents. Conjugate, think of it as the before and after. So the thing that on the left-hand side, on the reactant side of an equation, is a reductant, and therefore its conjugate pair would be the oxidant version of it. The skills that we have to be able to do in this is we have to write balanced half equations. Half equations are really important. We also have to be able to write overall equations. Once again, you should have seen some of that in year 11. If you can't recall it, that's okay. That's what we're here for. This is a summary of everything that we're supposed to know that came from a great source called Study On. I'd highly recommend it. But their little summary goes through some of the things that we need to know. I would recommend that you have a look through it. If you have a look, it's basically written from the study design. So you've got things like that oxidation or redox, that redox, sorry, that redox is electron transfer. We did that before. That oxidation is the loss. You hopefully remember that from last time, and hopefully you remember the idea of maybe not this bit, but certainly this middle bit. And we're going to add on for year 12 the start and end. So oil rig should be something you've come across in year 11. The an and the cat, never heard of it? Doesn't matter. We'll get there. The next thing I want you to know is that the oxidizing agent or the oxidant is something that is reduced. I know it feels backwards, but oxidation will not occur unless you put something in there to make it happen. An oxidizing agent is something that makes something else oxidize. It's therefore reduced. Therefore, the opposite is true. A reducing agent or reductant is oxidized. It feels backwards. You'll get caught out from time to time. The more you do, the more you'll get it. That brings us to the next bit. And the next bit is just getting started. So, number one, if we have to be able to recognize redox, well, there's three ways. I don't even know if that's spelt right. That's terrible. Um, let's try that again. Recognizing, which is a cool way of saying it. How's that? How do we recognize redox? Okay, three main ways. First way, once again, you've probably hopefully remember it from year 11. Let's call it the original, the old school. Let's call it the OG. The OG is where oxygen is involved. That's an N. Okay. If oxygen is involved, then it makes sense where the names came from. Oxidation is where something, usually a metal, gets some oxygen attached to it. So if I have a look at the old school definition, oxidation is where you pick up, gain oxygens. Oh, God. You gain some oxygens. Okay, I should have avoided the word gain, but they get more oxygens. So, for example, if you've got a bit of iron in your backyard, it sits out in the rain, if you're near the beach, it might get some salt attached to it, but mostly it's going to react with oxygen gas, The water and the salt will speed it up. And eventually that iron, whether it's on a car or a bit of garden furniture or something like that, it's eventually going to rust. Rust happens to be quite a complicated process, but rust is this. It's solid, it's flaky. This equation isn't balanced. We could probably balance it. You know what? Why not? So if I was to balance this, let's put a 2 there. Now I've got 6 oxygens on the right, so I'm going to need 6 on the left. I've got 4 ions on the right, so I need 4 on the left. There's a balanced equation. If I'm just looking at an equation like this, it looks to me like oxygen has been gained, oxygen's been picked up. Iron was on its own, iron has now got oxygens attached. That fits the definition of the old school original method of how to recognize oxidation. The flip side of it, well, reduction is where you lose some oxygens. So you had a bunch of oxygens attached. So if you had a bunch of oxygens attached to something, let's say you went mining and you got some bauxite out of the ground and it was aluminium oxide, we mine that and we want to turn that into pure aluminium so that we can sell it. The miners will dig this stuff up, we'll sell it as pure aluminium. We want to get rid of the oxygen gas that we'll get rid of and it will go off into the atmosphere. Once again, not balanced, so let's just fix that up. I'll do it in a different color. Let's fix that up. So now I've got 6 oxygens on the left. Let's go for 6 on the right. So that's a balanced equation. And just looking at it, this aluminium had some oxygens attached to it. It has now lost those. So you've reduced its reduction because you've reduced the number of oxygens. This is where the names came from. This is where the idea came from that redox, oxidation, and reduction was a thing because this is what people saw. As time went on, though, people saw that the exact same thing was happening even when oxygen wasn't involved. So while that very first method is still the original and still works and is still valid, it doesn't work all the time. If you don't have oxygen involved, well, you might have a problem. So we'll go on to the second way of spotting. And the second way of spotting is where you use an, last year, this, and once again, to spell out what they mean, oil, jeebus, I could spell, oxidation is loss. That's always where we stop. And what we should always remember is it's not loss because it can get confusing. It's like for the previous one, reduction was loss of electrons, loss of oxygens. Oxidation is loss of electrons. So this bit is really vital. Um, that gives us the oil bit. Now the rig bit is reduction is gain of electrons. This is the one we talk most about in year 11. This is the one that we really need to understand. It's really, really important. The problem with this one, why we don't simply use this one all the time, is it only really works if you can see the electrons. And by see, I don't mean that you can physically look at them, touch and feel them. I mean that you can see them written in the question. So if we go for an example, just make one off the top of our heads. Let's say I've got, let's say I've got my pen working. Let's say I've got magnesium. It's a solid. I do something to it and I turn it into magnesium 2 plus and 2 electrons. The idea here is I can physically see the electrons involved. I can see that electrons were there. And if we have a look at it, what kind of happened is we had this magnesium here. This is how it was. And it existed happily until something happened to it. We added something to it and it became this thing. It turned into this thing. In turning into this thing, these electrons were lost. So this is the loss of electrons. So using our statement, hopefully you get the idea that this lost electrons, therefore this is oxidation. And we'll go into it later what an and the cat is all about, but for now, as a little introduction, that an means that this oxidation would happen at something we would call the anode. That's really important when we talk about galvanic cells later on, and electrolysis. This is the best method for sure, but you really need to see the electrons so that you can tell whether they're being lost or gained. If they are on the product side, they are lost. If they were on the reactant side, well, they would have been gained. Maybe I could do an example of that. Let's go sodium as a plus. Some sort of reaction took place. Let's say he's aqueous. Some sort of reaction took place where he picked up this and it turned into solid metal sodium. In this example, this sodium ion existed. The sodium ion was sitting there until it gained these electrons. And if it gained electrons, then it's Rig, it's reduction. It can be hard, it can be confusing. There are 3 separate methods, all of them valid, all of them important, all of them useful. The second method, really important, an oil rig cat, really works beautifully well as long as you can see the electrons. If you can't see the electrons, it can make it quite tough. Let's take ourselves now to the third method. The third method, hopefully you kind of sort of remember from year 11. Then the third method is oxidation numbers. And oxidation numbers is the final way that we're going to recognize whether reduction or oxidation or neither occurred. Oxidation numbers have got a few rules. They're rules that might be hard to kind of memorize, but they are rules that once you get, they kind of flow and they kind of make sense. So the first rule I want you to kind of think about, number 1, is that an atom or compound, I should have said a neutral. Let's add it in now and pretend I never made a mistake. A neutral atom or compound adds up to 0. Once again, doesn't make sense until you do a couple. So let's do a couple. Let's say I'm sitting here with, as I am, I'm sitting here with pure solid gold in my pocket. It's gold, it has no charge, it's neutral. That means that the oxidation number of gold is 0. Okay, I'm sitting here breathing in some oxygen gas. That oxygen gas is neutral, it's a compound, it's going to add up to 0. If I wanted to put some sodium chloride into my water just to add a little spark, then this is a compound, it's neutral, so as a group, the sodium and the chlorine are going to add up to 0. Whatever you've got, it's going to add up to 0. I guess that leads us on to the next thing. Well, what if it's not neutral? All right, if it's not neutral, we would call it an ion. So, idea number 2, ions add up to their charge. Okay, once again, might not make sense until we do a couple. If you need more, give me a shout and I'll do some more. But for now, let's do some ions that I can think of off the top of my head. Let's do fluoride. Fluoride is an F minus. It becomes a minus because it's got 7 in its outer shell. The octet rule says it wants to be full. It's going to steal an electron. If fluoride exists, then it's an F minus. Therefore, its oxidation number will be -1. That makes sense, hopefully. If it doesn't, let's try another one. Let's go for calcium. Calcium ion has got a charge on it of +2, or 2 plus, sorry. So its oxidation number is going to be +2. Hopefully that's pretty simple. The flip side, or not the flip side, um, next, what if I had a polyatomic ion? What if I had a group that was an ion? So let's do, I don't know, SO4 2 minus. What that means is that this group, this S and four O's joined together as a group have gained 2 electrons. They're a gang that's stolen 2 electrons. What I know is that this, as a gang, as a group, is going to have an overall -2 as its oxidation number. If we do another one, let's do a positive one. This is ammonium. Ammonium as a group, 1 N and 4 H's as a group have lost 1 electron. They've become a positive. What that means is they're an ion. As the group, their overall charge is plus. Therefore, their overall oxidation number is plus 1. That's the second thing to try and remember when you're doing this third method. Go to the next one. The next rule is kind of the hardest to make sense, but once you get it, it really does make sense. Oh, this is wonderful. So the idea is if you know the charge, you know the oxidation number. It doesn't kind of make sense when you say it like that. So let's do a couple of examples. If I know the charge, I know the oxidation number. So let's do maybe one of the ones we did before. Let's do sodium chloride. Sodium chloride, we said, is neutral, so the whole lot has to add up to 0. Its oxidation number, its total oxidation number of that compound is 0. If I know the charge, then off the top of my head, if I know the charge, then I am going to be able to tell you what the oxidation number is. Hopefully some of you have come across NAs and CLs enough in your science and in year 11 to just recognize almost instantly what's going on here. For example, you might have seen chlorine enough to know that it forms Cl-. It does so because it's in group 17. Therefore, if this chlorine, when it's joined up to something in an ionic bond, is going to be a Cl- in there, then we can assume that the oxidation number of that individual inside this neutral compound is -1. Therefore, the sodium will be +1. +1 and -1 is going to add up to 0. The concept there is the whole lot will equal 0, and the individuals will add to 0. Let's do another one that's a little bit harder. Let's say I've got an ion, SO4 2 minus. The concept here is this is going to add up to -2. As a total, as a group, it will equal -2. I look at S, I look at O. I don't know S's charge off the top of my head. I haven't seen it enough. Incidentally, it does change a bit, so it does make it difficult, but I should know by now oxygen. Oxygen is in group 16. Oxygen is going to form an ion, which is a 2 minus. That means the individual oxidation number of oxygen is -2. Here, if this is -2, and I've got 4 of them, that means overall this is -8. Now, just having a look at this, I know that I need -8 and some other number that's going to give me -2 as an overall. So if we put it in here, we're going to get +6. That means the oxidation number of the S in this situation is +6. I hope that makes sense, because if it doesn't, I can do more. Let me know. There are some questions from the book that I'll show you in a moment. And if you are ready, you can go and do some of those questions. If you do get it, feel free to pause and rewind and contact me. But it's probably time to look at exceptions. The unfortunate thing is whenever we make a rule, we find out there's an exception to it. And that's because as scientists, we're trying to explain the world around us, not make rules for it. So if I was to do a very simple one to start us off, one that is not an exception. If I did H2O, it's neutral. It adds up to 0. Now, these are two atoms that I should know the ions off the top of my head. I should know, for example, that O forms an O2 minus, and I should know that H forms a H plus. These are things, what's the minus? These are things that I've seen enough in my science. These are things that I recognize. So if we put those two things together, if O is a minus 2, and I think hydrogen is a plus 1, well, I've got two hydrogens. Oh, don't know if you'll hear that noise. If I've got a plus 2 and a minus 2, then hopefully you'll oh, did you see that? Sorry, I'll have to pause.